Section 1.5 Transformation of Functions. Learning objectives. In this section, you will graph functions using vertical and horizontal shifts, graph functions using reflections about the x-axis and the y-axis, determine whether a function is even, odd, or neither from its graph, and graph functions using compressions and stretches. When we add positive number to a graph's output, we shift the graph up by that constant amount, as in the graph to the left. So what do you think happens when we subtract a number? So let's graph f of x minus 1 on the same plot to the left. So given here, this is f of x, the blue graph, and this is the graph of the cube root of x. And if you add 1, you go up by 1. So that's why you have it here. And what happens when we subtract a number? F of x minus 1. So remember, this is your y. So we go down minus 1, meaning we go down by 1. So it's going to be something like this. So that is vertical shifts of a graph. Next, horizontal shifts. When we add positive number to a graph's input, we shift the graph to the left by that amount. So let's use the same graph here of cubic function. So cube root of x is the blue. If we add 1, f of x plus 1, that is 1 to the left. So what do you think is going to happen when we subtract a number? So let's graph f of x minus 1 on the same plot to the left. This minus 1 here, this is now 1, meaning 1 to the right. So we move this 1 to the right. So something like that. Okay, so take note. Look what's happening here for vertical and horizontal shifts of a cube root function. So number 1, if it's x plus 1, meaning that is cube root of x plus 1, and x plus 1, that is meaning 1 to the left. Okay, if it's f of x minus 1, that is simply cube root of x minus 1, and that 1, that is 1 to the right. You see x plus 1, it's 1 to the left, x minus 1, 1 to the right. So just to do this again, here, square root of cube root of x minus 1, so meaning that is down, and f of x plus 1, that is cube root of x plus 1, is you go up by 1. Example number 3, the graph below is a transformation of the toolkit function f of x equal to x squared. Find a formula for the transformation. So what happens here? So a parabola for f of x equal to x squared is this. So what happened here from here to the right 2. So that is 2 units to the right. So f of x is equal to x minus 2 squared. That is 2 units to the right. So by the way, this is your assignment of using decimals. You're going to transform parabola. You're going to need to show that you know how to move it to the right, like this, 2 to the right, or to the left, or you go up, you go down, and later on, how about a combination of both, to the left, to the right, up, to the right, up, or to the right, down, to the left, up, or left, down. Okay. Quick check number 1. Graph toolkit function of f of x equal to square root of x. So when we graph this, square root of x is like this. And the transformation g of x equal to square root of x plus 2. X plus 2 meaning 2 to the left. On the same set of axes, is this a horizontal or vertical shift? So that is 2 to the left. So 1, 2. So that is a horizontal shift. How many units was the graph shifted by? 2 units to the left. Next, another toolkit function, f of x equal to absolute value of x. And this is absolute value of x is the v, and we're going to sketch a graph of h of x equal to f of x plus 1 minus 3. So this x plus 1 meaning 1 to the left, and then here minus 3 meaning down 3. So let's do that. So we move this v-shaped 1 to the left. So let's say this is the vertex, 1 to the left and down 3. 1, 2, 3. So everything, the whole graph, you move it 1 to the left and down 3. So this is the graph. So we can write it in terms of the absolute value as absolute value of x plus 1 minus 3. So this is your h of x. Okay. Next, reflections about the axis. So given an exponential graph here, so horizontal reflection is this about the y-axis, and you have the vertical reflection about the x-axis. So example 5, reflect the graph of s of t is equal to square root of t. Square root of t is this graph vertically and horizontally. So letter A, vertical reflection from negative s of t to negative square root of t. So vertical reflection is from here to here. So that is about the x-axis. Then horizontal reflection, again, this is the square root of x. That becomes this. That is about the y-axis. You reflect it about the y-axis. So let's have another example here. Let's say cubic. So we know that the cubic graph is like an S. So if we want y equals negative x cubed, so how do we graph this? So that is a reflection about the y-axis. So you will have like this. How about y equals negative x cubed? You see the difference between the two. Number one is negative x cubed here, and number two is quantity, or inside the parenthesis, negative cubed. And negative x cubed is still equal to negative x cubed, and the graph here is horizontal, so you will have this. So when it's outside, vertical, negative inside is horizontal. So take note of that. Negative outside is vertical. So imagine there's a reflected vertically, and this is horizontally. Next one, add an even functions. A function is called an even if for every input f of x is equal to f of negative x, and a function is called an add function if f of x is equal to negative of f of negative x. Visually, a graph is even if you can turn your paper over the x-axis and get the same graph looking back at you. And a graph is add if you can rotate your page 180 degrees and see the same graph again. So let's take a look at these examples here. Which of the following graphs are even, odd, or neither? So this is a cubic x cubed, f of x equal to x cubed. You can turn this 180 degrees and you will see still the same graph. So that's why this is an odd. Another way to look at this, since it's 180 degrees, if you can reflect it both about the y-axis and about the x-axis, and you still see the same graph, then it is an odd function. How about the next one? Y equals the absolute value of x. So here, if you can turn the page over the x-axis and get the same graph looking back at you, and look at this. This, let me use a red. This is the same as this. Same image, right? So it is an even function. How about the third one? This, you don't see this on this side, so definitely not an even. And can you turn this into 180 degrees and you will still get the same? No. So this is not an even, not an odd function. Okay, that's what you do when you have graphs. How about when you have a given function? So is the function f of x equal to x cubed plus 2x even, odd, or neither? So what do you do here? Whenever you do this, all you have to do is substitute negative x. F of negative x, solve for f of negative x. So that means you plug in negative x to the x. So negative x cubed plus 2 times x. What is negative x cubed is negative x cubed. 2 times negative x is negative 2x. You can factor off a negative here. So this is x cubed plus 2x. And as you can see, your f of x is equal to x cubed plus 2x. So that is equal to negative of that. Negative of f of x. And remember, if f of negative x is equal to f negative of f of x, so this is odd. So take a look at these stretches, vertical stretches and compressions. This is the regular parabola. if it's greater than 1, like this one, the green, it's 2 that's greater than 1, it's vertically stretched, it's become skinnier. If it's 0.5, see, this is half of that, so that is a vertical compression. Sorry, this is not a parabola. Next one is, this is a parabola, and horizontal compression is the green one. That is when it is greater than 1, and here 0.5, that is the horizontal stretch. All right, summing up, take note of this, all of this. So vertical shift and down k units, that is f of x plus or minus k, like f of x, oops, sorry, let's say y is equal to x squared plus 2, or y equals x cubed minus 3. So those are vertical shift up and down k units. And then horizontal shift left to right. So it's like if you want the function f of x equal to x minus 3 squared. So that is 3 to the right. Or let's say if you want f of x equal to absolute value of x plus 2, that plus 2 meaning that is to the left. And then vertical reflection, negative in front of f of x, that is outside by a vertical, and inside, negative inside f of negative x, then that is horizontal reflection. And then the last two, take note of the stretch factors. So a, if it's greater than 1, that's a vertical stretch. If it's between 0 and 1 is a compression. And the last one, f of b of x, if b is greater than 1, that is compressed by 1 over b. Take note of this. And if it's between 0 and 1 is a stretch by 1 over b. Let's have some examples. Graphical. For the following exercises, use the graph of f of x equal to 2 raised to x shown in figure 31 is an exponential to sketch a graph of each transformation. So this is an exponential function, 2 raised to x. 24, 2 raised to x plus 1. Plus 1, meaning you go up by 1. Minus 3, meaning you go down 3. Minus. Then 2 raised to x minus 1 is, that is 1 to the right. So let's do that. Up 1, it's green, so we go up 1. And then down 3, the orange, 1, 2, 3, should have something like this. And then 26, red, you move this 1 to the right. Okay. Then the next set of problems, and the last problems. For the following exercise, use the graphs of transformations of the square root to find the formula for each of the functions. So you know that the square root function is like this. So this is a vertical reflection. So that is So this is y equals negative square root of x, square root function. So definitely this is this red, I'm going to use red, is negative square root of x. And remember, this is a vertical reflection. How about this? From this given y equals square root of x, this is inside. So square root of negative x. And remember, if it's inside, we call this as a horizontal reflection. And that's it for section 1.5. Next section, 1.6, absolute value functions. A V-shape. In this section, you will graph an absolute value function and solve an absolute value equation. The toolkit function with the transformations of the absolute value function looks like a V. This is absolute value function. Now let's graph f of x equal to 2 absolute value of x minus 3 plus 4. So here, remember, minus 3 meaning 3 to the right, plus 4 is you go up 4, and 2 is a stretch factor. So let's do that. If we move it 3 to the right, 1, 2, 3, and then you go up 4, 1, 2, 3, 4, and then that's a vertical stretch. So it's going to look like this. So that is the graph of f of x. So we're using here, since it's an absolute value function, in general, it is f of x equal to a times the absolute value of x minus h plus k. So this a is the stretch factor. Hk is the starting point. And h, like what we did for number 1, is either to the left or to the right. K is up or down. So this time, given the graph example number 2, so we want to find that equation. So here, the original absolute value function from the origin is the v. So if you notice the transformations here, you move this 3 to the right and down 2. So when you move it 3 to the right, that is x minus 3, down 2, so minus 2. And we have a. How do we solve for a to get the exact equation of this blue absolute value graph? So to find a, all we need to do is plug in a point that is on the graph. On on the graph. So what do we have here? We can have, how about this point, or you can have this point or this point. So let's say this point is 4, 0. So this is your x and this is your y. So we plug in that here. So y is 0 is equal to a absolute value of x. X is 4 minus 3 minus 2. And then we add to both sides. So that is 2 equals a 4 minus 3 is 1. Absolute value of 1 is equal to 1. So a is equal to 2. So you can write now the equation of this absolute value graph is f of x is equal to 2 times the absolute value of x minus 3 minus 2. Okay. All right. Since we graphed the absolute value function and we wrote an equation of an absolute value function given a graph, this time we're going to solve absolute value equations. So there are steps to solving an absolute value equation. The first one is isolate the absolute value. And then all you have to do is get two equations by setting the other side positive and the other one negative. And then solve both equations. Okay? Let's do this. Example 3. For the function f of x is equal to absolute value 4x plus 1 minus 7, find the values of x such that f of x is equal to 0. That is, meaning the zeros of f of x. So isolate the absolute value. So let's f of x is 0. So let's do that. Absolute value 4x plus 1 minus 7 equals 0. So finding the zeros. First step, isolate the absolute value. So meaning should add 7 both sides. So 4x plus 1 equals 7. And then get two equations. I'll write it here. One is positive and one is negative. So 4x plus 1 equals 7 and 4x plus 1 equals negative 7. See, one is positive, one is negative. And then now solve for x. So subtract 1. So 4x is equal to 6. And when you divide by 4, x is equal to 6 over 4 or 3/2. Then the other one, subtract 1 both sides. So that is 4x negative 7 minus 1 is negative 8. And we divide both sides by 4. Negative 8 divided by 4 is equal to negative 2. So these are the answers. Okay, let's try quick check number 2. For the function f of x equal to the absolute value of 2x minus 1 minus 3, find its 0. So 2x, absolute value of 2x minus 1 minus 3 is equal to 0. Then get two equations by setting the other side positive and the other side negative. So say here 2x minus 1 minus 3. Oops, sorry. You can do this, but we need to isolate this first. So that is by adding 3 both sides. and then now get two equations. One is positive and the other one is negative, and then solve for x. So add 1, so x, then divide by 2, so x is equal to 2. Add 1, then divide by 2, x is equal to negative 1. Now, will there always be two answers when solving an absolute value equation? Not always. Example number 4. Solve 1 equals 4 times x minus absolute value of x minus 2 plus 2. So 1 equals 4 times absolute value of x minus 2 plus 2. If we isolate the absolute value, so subtract 2 both sides. So negative 1 is equal to 4 absolute value of x minus 2, and then we divide both sides by 4. So this is negative 1/4 is equal to the absolute value of x minus 2. But this is negative number, and take note of this. In general, for the absolute value should be greater than or equal to 0. It can never be negative. Okay. Okay, I'll give you an example here. So let's say y is equal to absolute value of x minus 3. If you graph this, x minus 3, that is 3 to the right. So look at all the y values here. Everything is above 0. Everything is positive from 0 and above, never negative. Do you agree? Okay, more examples. For the following exercises, solve the equations below. So your goal is always to isolate the absolute value. So get rid of 2, so divide both sides by 2. So this is absolute value of 4 minus x is equal to 7/2. And then now to remove the absolute value, you have to get two equations. One is positive, one is negative. So 4 minus x is equal to 7/2. And the other one, 4 minus x is equal to negative 7/2. So solve for x. If we add x both sides, same thing here. Then if you subtract 7/2, here you add 7/2. And 4 minus 7/2, 2 times 4 is 8, minus 7 is 1/2. So that is 1/2. And here 2 times 4 is 8, plus 7 is 15. So 15/2 is equal to x. So that is number 14. 21. Absolute value of 3x minus 1 is equal to negative 7. Remember, this is negative and it can never be equal to a negative number. So no solution. Again, don't forget, absolute value can never equal a negative number. Next, graph the given function by hand. You can start with a toolkit function of the absolute value function and then use the transformations. So this is very important to know for the transformation, especially when you work on the Desmos activity lab assignment. So since it's an absolute value function, oops, I'm going to use black. If we start with a graph of an absolute value function, the toolkit function, number 42, y equals negative square root of x minus 2. Minus 2 meaning down 2. Negative, that is a reflection. So all you have to do here is you go down 2 and you reflect it. So this is the answer. 44, let's do the same thing. Let's have an absolute value function here, and then here with the transformations, minus 2 again, that is down 2, x minus 1 meaning 1 to the right, if it's minus to the right, if it's plus to the left, and then this is a reflection. So let's do that. You move it 1 to the right, then down 2, and then a reflection, something like that. And that's it for section 1.6. Next, section 1.7, inverse functions. Here you will verify inverse functions, determine the domain and range of inverse functions, and identify the one-to-one functions, and restrict domains to make functions one-to-one. Okay, any one-to-one function f of x, what does one-to-one mean again? It has an inverse. By inverse, we mean a function that undoes whatever f does. So that is, for a one-to-one function, there is another function which we will call f inverse of x, that has the property of f inverse of x is equal to x, or f inverse of f of x is also equal to x. This is like, we cancel this, is equal to x, with this is equal to x. And take note that f and f inverse undo each other. And don't confuse the notation raised to -1. It doesn't mean reciprocal. So f inverse of x is not equal to 1 over f of x. Okay. Some common functions and their inverses. 2x, f inverse of x is x over 2. F of x equal to x over 3. F inverse of x is 3x. Square root of x, that is x squared. X cubed is cube root of x. And cube root of x, you can write this as x raised to 1/3. And how about the absolute value of x? Actually, no inverse. Okay, for example, f of 4 and absolute value of 4, and absolute value of 4 is 4. But f inverse of x is not equal to negative x. So this is wrong. Okay, let's have some example here. For a particular one-to-one function, f of 2 is equal to 4, f of 5 is equal to 12. What are the corresponding inputs and outputs for the inverse function f inverse of x? So f of x, so you have 2, 4, and 5, 12. For f inverse of x, it's just going to be 4, 2. I'm going to use red. 4, 2, and 12, 5. So what do you notice here about the inverses? You're just switching x and y. So don't forget. So inverses swap x and y, and the x are the inputs and y are the outputs. Okay, so take note of this. This is very important. So inverses swap x and y, or inputs and outputs. Next, how to test whether functions are inverses. So remember, the inverses undo each other. So if you want to tell if f and g are inverses of each other, then we must determine if f of g of x is equal to x or g of f of x is equal to x. You don't need to show both, you can just show either of the two. So let's say example number 2, f of x equal to 1 over x plus 2 and g of x equal to 1 over x minus 2. So let's use number 1. So we're going to show that is f of g of x equals x. So that's the question. So remember, you don't need to show both. You can just choose one. So let's try f of g of x. And that is equal to your g of x. Substitute that to the x of f. So your f of x is 1 over x plus 2. So you're going to change your x here with your g of x. So this is 1 over x minus 2. So let's simplify this. 1 over x minus 2 plus 2, negative 2 plus 2. So this 1 over x. Get the reciprocal of this. So that is equal to x. And you got x, so yes, they are inverses. Okay, so don't forget, if you try f of g of x or g of f of x, and if your answer is x, meaning they are inverses. Let's try another example here. F of x equal to x cubed and g of x is equal to 1 over 1/3 of x. You're gonna try g of f of x. So that is, with g, your f of x is x cubed. Then we're gonna plug in x cubed to x of g of x. So this is x cubed, and 1/3 of x cubed is equal to x cubed over 3. And look at this, we didn't get an x, so this is not an inverse because this is not x. So we can say here that f and g are not inverses. Okay, f and g are not inverses. Okay, next, find the domain and range of inverse functions. So remember, important for inverse swap. So meaning your domains and range swap also. So like here, the domain of f becomes the range of f of inverse, and then the range of f becomes the domain of f of inverse. So don't forget inverses swap. So the inverse they swap domain and range. So since inverses swap domain and range, let's answer example number 4. Find the domain of one-to-one function f is 1 to infinity, and the range is from negative infinity to negative 2. Find the domain and range of its inverses. So given, I'm just going to write the given here. Domain is from 1 to infinity, and range is negative infinity to negative 2. So this is for f. And then for f inverse, so remember inverses swap. So this is going to be the range. So this 1 to infinity, and this is going to be, the range here is going to be the domain. That is from negative infinity to negative 2. Okay? So make sure that we understand the what inverses mean and how to use the notation correctly. All right, next one. We don't need this. Let's skip this. Number 6. A function g of x is shown below. Find g of 3 and inverse of 3. So what is g of 3? G of 3 is this point that is equal to 1. The next is, what is g inverse of 3? So here, remember it swap. For inverses, you swap the inputs and the outputs. If this is x, if x is your 3, then that becomes y. So if this is your y, and then now the answer is this. So that is equal to 5. So that's why, that's how the easiest way to get the g inverse of 3. So you swap, this is your x, this is y. So you swap, this becomes the y, and then so find the x value, and the x value is 5. So that is the answer. Next, solving for inverse functions algebraically and restricting domains. So to solve an inverse, it's pretty straightforward. Make sure f is a one-to-one function, solve for x, interchange x and y. So given example number 7, f of x equal to 2 over x minus 3 plus 4. It's easier if we write this as y equals 2 over x minus 3 plus 4. And then as you want to solve for the inverse, next thing to do here, you can switch x and y. So this is now x equals 2 over y minus 3 plus 4, and then solve for y. We need to isolate y. So next is subtract 4. So x minus 4 is equal to 2 over y minus 3, and then, sorry, I don't have space. You can cross multiply this, and you can multiply this too. So let's do that. I'm gonna write it here. X minus 4 times y minus 3 is equal to 2. And then I can divide this by x minus 4. So this is y minus 3 is equal to 2 over x minus 4. And then add 3. So you add 3 both sides. So that is, sorry, I don't have space. Y equals 2 over x minus 4 plus 3. Now after you solve for that y, that is now the inverse. So f inverse of x is 2 over x minus 4 plus 3. Okay, so again, look at what I did here. Given f of x equal to 2 over x plus 3 plus 4, I wrote it in terms of y equals to 2 over x minus 3 plus 4, and then switch x and y, and then I isolate y, solve for y, and then that y is now your f inverse of x. Okay. Next, number 8. Find the inverse of the function f of x equal to 2 plus square root of x minus 4, as well as the domains of f and f inverse. So 2 plus square root of x minus 4. If you're going to sketch this, that's an square root function. X minus 4 meaning 4 to the right. 1, 2, 3, 4. Then plus 2 is up 2. So this is the shape of a square root function. So what is the domain of this? This is 4, this is 2. So based on this graph, it starts at 4. So using the interval notation, so from 4 to infinity, and your range, the y values, the outputs, it starts at 2. So that's 2 to positive infinity. And then how do we get the domain of f inverse? But before that, we need to solve for the inverse of f of x. Let's do that. So remember, the first step here is, let's write this as y equals 2 plus square root of x minus 4. What's the next step? Switch x and y. X is equal to 2 plus square root of y minus 4. Then isolate y. So subtract 2. So x minus 2 is equal to square root of y minus 4. And then square both sides to get rid of this square root. So x minus 2 is equal to y minus 4. And then last is we add for both sides so that this is equal to y x minus 2 squared, plus 4. So that is the inverse. And what is the domain? So meaning you swap the range and the domain. So meaning it is going to be from 2 to infinity. Okay, next. Given a graph, you're going to evaluate this. Find f of 0. F of 0 is this, so this is equal to 3. Solve f of x equal to 0. And to do that is, meaning when does y equal to 0? So this one, f of x is equal to 0, meaning when does y equal to 0? That is when x is equal to 2. So that's number 26. 27, f inverse of 0. That means also this is when does y equals to 0. Same thing. And this is a y value. And remember that. That's a y value because it's in the inverse, f inverse of 0, that becomes a y value. And the answer is when x is equal to 2 also, the same. Now solve for f inverse of x is equal to 0. That is when does x equal to 0. So meaning f of 0 is equal to 3. Okay. Next, for the following exercises, evaluate or solve assuming that the function f is 1 to 1. So f of x equal to 7. What is f inverse of 7? So f inverse of 7 is equal to 6. What do we do here? Remember, you swap x and y. This is x, this is your y. So that becomes now your x. Well, you swap. Next, 34, f of 3 is equal to 2. What is f inverse of 2? Is equal to 3. Yes, that is correct. You swap x and y. Algebraically, if you want, I'll show you number 34. It's the same thing for number 33. So f of 3 is equal to 2. Then if you want to get the inverse, f inverse, so it's like you get the inverse of this, both sides. So that's why now this is 3 is equal to f inverse of 2, which is this. Okay. Last problem. To convert from x degrees Celsius to y degrees Fahrenheit, we use the formula f of x equal to 9/5 x plus 32. find the inverse function if it exists, and explain its meaning. So f of x equal to 9/5 x plus 32. So let's write this as y equals 9/5 x plus 32. Then we can switch x and y. X is equal to 9/5 y plus 32. Solve for y. Subtract 32, x minus 32, and then you multiply both sides by the reciprocal of 9/5, so 5/9. So this is 5/9 of x minus 32 is equal to y. So meaning the f inverse of y is equal to 5/9 over x minus 32. Explain its meaning. So we can say that f went from Celsius to Fahrenheit. So our f inverse goes from Fahrenheit to Celsius. Okay, and that's it for 1.7. Thank you.